Good. Hope you had a nice weekend. Mine was great until the alarm clock went off this morning. I was like, really? Oh. But that's Monday for you. So, go ahead and get your clickers out. We'll review some of this momentum stuff. See what stuck, what didn't. All right, here's the first question. Polling's open. Whoop. Basically, a cannonball shot from a cannon. It either has a long barrel or long barrel, that implies relative short. Okay, so much for trying to just read it, Adam. A cannonball shot from a cannon with a long barrel will emerge with greater speed because the cannonball receives a greater what? Is it getting a greater average force, impulse, neither, or both? See what you remember, what you think. All right, 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we're split. All right, mostly between B and C, about 41% each. So you either think it's impulse or both. Okay, I'm going to do a little demo to help answer this before I tell you the answer. So I've made many a marshmallow shooter, so I was proud to whip this up for class. PVC pipes. I'm going to put they're beyond their prime, mini marshmallows, which actually helps in this demo. They're nice and hard now. If I put one on this end and blow, you can figure out what's going to happen. I'm going to apply a force to this mass, and it's going to accelerate it. And it'll come out with a muzzle velocity at some speed, depending on the force I do, its mass. And we go, it comes out pretty good. Now, I'm going to stick one right here, and on the other pipe, I'm going to put it at the very end. I'm going to put my mouth around both and apply the same force to each tube. Which one do you expect to go farther? The one that's mounted near my mouth, or the one away from my mouth? Near. Okay, just because I heard more nears. Why? Somebody tell me why.
Well, it'll just have more time for its momentum and more time to accelerate.
More time.
Acting on it for longer.
More time to accelerate. Anybody want to add to that or adjust? The more time you add on to it, the greater the average force will be. And yes?
By the time that your air reaches the one on the end, the pressure has already...
By the time my air gets to the end, the pressures might be a little less. There is some truth to that. Okay, let's do it. In case you can try to keep track, the one that's closest to my mouth is closest to you. Anyway. Hopefully that was conspicuous enough. Yeah, the one that was towards the end only made it this far, not as fast. Where the one near my mouth did cruise like initially we saw. And the explanations that were stated were correct. If I'm applying the same force, roughly, to both ones, then this one has all of this time to accelerate. So you can think of it as a collision in reverse. I'm applying a force to it and causing this guy to change his momentum. If I apply a force for a longer amount of time, then I can get it to accelerate more. It'll get to a higher velocity, muzzle velocity when it comes out. Does that make sense? Because I like marshmallows. Let's do it again. Whoa, that was good. Don't breathe in while you're in. I have another demo. I do this with cornstarch. I learned it with that one, but I forgot about this one. Okay. Yeah, big difference. So back to the cannonball one. I think I hope you're all convinced that it definitely is A. No, it's at least definitely A. The answer is B. Impulse.
If it had the same force, which means the same average force the whole time,
That's a tricky question. Yeah.
I admit I'm being a little facetious when I said it was definitely A, because you guys didn't seem awake yet. It backfired. I apologize. The answer is B only. Because back with this one, I was trying to apply the same force to each one. Somebody said the average force is going to be greater. Go ahead.
Okay, wouldn't the average force be larger because you're acting on the marshmallow in the long barrel for a longer amount of time?
How does that increase the force?
Well, since you're using the same amount of force throughout a section of time, it's going to act longer on the marshmallow than it is on the one that's just sticking out of the barrel.
Good. I'm glad you said it that way. And I was being a little tricky here to prove a point. I'm hoping it's not going to keep backfiring. You even just said that you apply the same force, but for a greater amount of time.
Yeah.
That means the force on average was the same throughout, right? We're going to say that throughout on average it had a certain force. That force is the same as the other one. It was applied for the same amount of time in each barrel, but the marshmallow that started near my mouth gets to feel that force for a greater amount of time. It doesn't feel more force. It just feels it for a greater amount of time. Yes?
So wouldn't the average force be larger?
The average force is, if the force were like great at the beginning and less at the end or something else in the middle and it kind of changed throughout time, we'd say on average it was such and such. If we could simplify and I could apply a constant force the whole time, then that would be the average. In reality, that doesn't happen. That's why we were saying average force. But the average force on each tube is the same. If I happen to blow harder at the beginning than I do at the end, or vice versa, the average is still the same for each tube. It's like driving your car back to velocity. You go 10 miles an hour, then you go 50 miles an hour, then you go 20, and then 75. On average, we'd say you're going, whatever that works out to be, how long you did it, but a certain, we could call it 40 miles an hour. And so you'd get the same result if you applied went 40 miles an hour the whole trip. That's how we'd say average. My point here again is that the force is the same on both sides, but if that force can be applied to the more time, to one of the marshmallows, it will feel it gets accelerated for a longer period of time and thus gets up to a higher speed. Okay, now I saw some hands. There's one over here first, I think.
So does the one that's in the barrel longer experience a greater force, but it's just divided by time? So the average is the same?
It does. The one in the that spends more time in the barrel feels the exact same force as the other one, but it feels it for longer.
I was just going to say, feeling it for longer, that's actually impulse, like 4 times.
And that's why the answer is impulse. Yes, feeling force for a certain amount of time, the product of force and time is impulse. That's why the F, the force is the same, even on average, but the force over a longer time, which is impulse, You get a greater time, you get more impulse. And impulse changes the momentum. The marshmallow that started near my mouth has a greater change in momentum because it had a greater impulse. There's hands over here.
So if you just took that PVC pipe and just cut it straight in half, that force would make no difference. The force is just still the same.
Yeah, if I'm trying to blow the same, I can't. But yeah, I'm trying to apply the same force to both. And I'm the first to admit that I'm sure I'm not applying a consistent force. That's why we're looking at the average. But it's the same average for each pipe that I'm blowing, force applied. It's just the marshmallow at the end leaves. As soon as I start blowing, it leaves. And thus, the other marshmallow is still in the tube and gets that force. It's still feeling a push. The same push, but for a greater time. The other one's already left, and it doesn't feel the push anymore.
So for this question, it not necessarily depend on
So yeah,
the cannon itself, the length of the cannon doesn't, the force is the same.
yeah. So but to this one, the cannonball, it's like the same cannon, whether you made it a long barrel or a short barrel. And it's assuming that the cannon's going to apply the same force to both. And that's what I was asking you. I didn't expect you. That's why we didn't state it implicitly. But if you do that, you put a longer barrel on something, it's the same with a rifle. If you cut the pipe off the rifle, the gun will still apply the same force to the bullet. But if you put it through a long tube, now those gases can push on that bullet for a longer time and get it up to a higher muzzle velocity. A greater change in momentum, a greater impulse. One over here.
I'm perplexed by the use of the word impulse rather than the word momentum. I thought impulse was something to change momentum. And while here we're talking about which does the cannonball get greater momentum if it has a longer barrel?
Yes. The marshmallow, the longer barrel will give the cannonball, it will get to a greater momentum, which means it received a greater change in momentum because it received a greater impulse. And impulse is because it received the same force but for a greater amount of time. Work backwards. Same force for the same amount of time, that's impulse. It received a greater impulse. Impulse is a change in momentum. It provides a change in momentum. A greater impulse will get the thing to change its momentum more. Thus, it will end up with more, well, if they started with the same momentum like they did in this case, 0, it'll get up to a larger momentum at the end. Is this helping? I chose this example to try to differentiate more the difference between force, impulse, and momentum, because they are 3 different things. Did that help?
I've understood from other examples that when you have a cannon that fires a shell, that the principle of conservation of momentum says that the momentum of the bullet is offset by the momentum of the cannon itself. They cancel each other out.
That's correct.
But I thought impulse was something that was used to change momentum.
That's correct. Let's do it while we're on it.
Cannon is creating momentum, and then once it's created, impulse changes it.
So he's talking of like a gun or a cannon that shoots. And he understands from conservation of momentum, which we haven't got to yet in this chapter, that this is something that I'm going to use for it. A little cannon, it's spring-loaded, and I have a little cannonball I can put in there. And when it shoots, this exerts a force on the cannonball. From Newton's third law, we know that the cannonball exerts an equal but opposite force back on the cannon, correct? The force is the same in magnitude, Newton's third law. That force is applied for a certain amount of time. That's what we call impulse. So this is providing an impulse to this, and this is providing an impulse to this. An impulse produces a change in momentum. So this has a certain mass, and this has a certain mass. Initially, you probably know this, their momentum is Zero, because they're not moving. Momentum is mass times velocity. So they both have momentum 0. After it shoots, what do you expect to happen? This flies this way. It now has momentum because this guy's impulse that he imparted on him changed this guy's momentum. And it makes it go from 0 to something. That impulse will equal the change in momentum. And vice versa. The impulse this guy produces on this mass will change his momentum. And I would expect him to recoil at least a little bit. The beautiful part is, since we brought it up, and that's what I was going to cover today, conservation of momentum is another topic in here, and it means just that. Momentum is conserved if you consider everything involved. In this case, our system is the cannon and the cannonball. And initially, their total momentum, or as the book puts it, their net momentum right now, before the collision, it's kind of like an anti-collision, is 0. So what does the total net momentum have to be after the collision? 0. That doesn't mean each individual one can't be moving. Their momentum changed individually, but as the system, the total must be 0. Remember that velocity is a vector? This guy will have momentum that way, and this guy will have momentum that way. This guy's momentum will cancel this guy's momentum. They're equal in magnitude, but opposite in direction.
Oh, so the system, this is like kind of like the third law and stuff. The system as a whole doesn't move. Its momentum.
It is kind of like, I'm just repeating for Newton's third law, the system, yeah. I always like to say total momentum is always conserved. That way I don't forget you have to include everything that's involved. If I just look at this guy alone, it doesn't look like momentum's conserved because he started at 0 and he ends up at something. But that's because this guy was involved. And go back to Newton's second law that says, okay, this guy has little mass, so he's going to get accelerated more than the big mass. Thus, I expect this guy to be going faster than this guy. Is this helping? Trying to put all the terms together. So I'm going to extend this string back to here, load it, get rid of friction, because this guy's it's not a real cannon. So he's free to slide. We'll try to balance it here, if it's mostly level. And I'll cut the string and see what happens. Ready? Indeed, he does recoil, but his velocity is much slower than that. But this guy's momentum, you take his mass times his velocity, that will be equal to that guy's mass and his velocity. Equal in magnitude, opposite in directions. The total momentum, the net momentum, is still 0 for the system, just like it was before. You can use this to predict how fast something will go, because total momentum is always conserved. But again, this exerts a force on the cannonball. The cannonball, Newton's third law says, same force back on it. The force each one felt is the same. Before, we could have figured this out. Newton's second law, just like I said. The little mass will accelerate more than the big mass, just from Newton's second law. This applies with impulse and momentum too. It means the big guy won't get moving as fast as velocity. But their momentums will be the same. They both received the same impulse, same force for the same time. It made each of their momentums change the same amount. Little m to big V and big M to little v. Because the total momentum must be conserved. I'll stop babbling. Any questions about this or back to the cannonball?
I just want to make sure I understand. So the reason you put the air there was to remove the friction, and that's why it kept going.
Yes.
And it was the equilibrium was 0 or even or whatever you want to say. It would have kept going forever.
Yes, this would keep going forever because there's inertia.
Correct.
Yes. That's why I did the friction. There's so much friction right here that the cannonball is exerting a force back on this guy. True. But the frictional force is trying to keep him put. And you wouldn't have seen him recoil had I not eliminated friction or reduced it.
So it would have gone a little ways and stopped, probably just gone a little ways and stopped if you hadn't had the air.
Oh, it wouldn't have moved at all in this case. Yeah, because it was such a little force with a puny mass. But in real life, we see it with cannons. You can see you've seen it in Hollywood. The cannons shoot. Don't get behind one of those. Even friction with the ground can't resist that. But it'd be even more if there was no friction between the ground and the cannon.
I mean, the ball went that way and stopped because the air resistance or hitting.
Yeah, it hit the ground, and then a force was applied to change it, and I get to find it at some point. Yes, there's...
During the equation when the cannonball shoots the ball out, is momentum zero, or is it just zero after?
The total momentum before the system was zero. You see that? The total momentum after the system, including both, is zero. The individual moment, even during. As it's coming up. Yeah, if you took the total between both, it's always zero. Individually, they weren't. This gained momentum, but in opposite directions. Because an impulse was provided by that force for a certain amount of time. So back to this. If you apply a force for a longer period of time, you provide a greater impulse, which yields a greater change in momentum. Yes?
Is it possible that when there's a recoil, like an example where recoil, that the time interval would be actually different for the two bodies that are coming apart? So that, because we're saying that when there's an impulse acting on this, you just apply it to the spindle. So the same impulse is acting on the other.
Yeah.
That's a point that time is always the same for the two.
Yeah, he's saying if with Newton's third law applies, yes. When something's pushing on something else, the something else pushes back. The force is the same, the time will be the same.
Is it always the same?
Yes, when you have an action-reaction pair, yes. When it's different is if you go, like this one. It's two different bodies. I was applying the same force, but on two different things. Thus, the time applied for one was different than the time of the other, because that wasn't an action-reaction pair. It wasn't one pushing on it and it pushing back. Or when you compare two different cases, running into a brick wall as opposed to running into a haystack. Those are two different instances, so no, all bets are off. It could be different times or not. But, just to clarify, when I run into the wall, the force I put on it's the same as the force on me, and the time of the collision was the same for both of us. Thus, the impulses should be the same as well in that case. In the red behind you?
Yeah, I was just going to say that it's easier for me to see the math behind, like in regards to the pipe example, it just makes sense.
Yeah, that's a good point. Sometimes the math helps people more. Let's do this one first. So you had, there. So we'll have momentum big M, V, plus little m, V. We'll call it 1 and 2. And initially it was 0, because this guy's was 0 and this guy's was 0, so the total is 0. That tells us, I know now, total momentum 0, it's going to be 0 in the whole time, during the collision and after. After, this guy ends up going that way a little, and he ends up going that way a lot. So you get big M, V final. And this guy's little m, V final. Let's say to the left is negative, and to the right is positive, since we got two different directions now. So you add them up. And I still know it has to be 0. So if I know their masses and measure the velocity of one of them, I can tell how fast the other one was going. Let's approximate. make life easy. Let's say that's a kilogram, and it was moving 1 meter per second. The other guy, 1/10 of a kilogram, because he's small. So how fast did the little cannonball shoot out? Yeah, do you see that it would be 10? 1 times 1 is 1. This will be a negative 1. So this has got to add up to be a positive 1 to cancel to 0. And to do that, this would have to be 10. So yeah, the little cannonball ended up going 10 times as fast because their mass ratio was 1 to 10. Because they started together at 0. We're going to do more collisions too with the math. Don't let me not. Because that does help people. Now I'll do the cannonball in a moment.
Is the velocity you're using in this equation to be measured at the end of the barrel?
Yeah, right when it comes out, right when they separate. Yeah. Inertia says it would stay at 10 meters per second until something else acts on it.
The velocity we're talking about, these formulas for impulse, for example, would be measured at the end of the barrel.
Yes, yes. Yes. At the end of the barrel, we would measure. These were at the beginning before they were moving at all, but they could have been. We'll do some examples differently. And yes, this is as soon as they separate, as soon as it comes out of the barrel, and there's no longer a force being applied or an impulse, force for a given amount of time. The time's done. They've separated. We're looking at it right then.
So to go back to the point that was raised a moment ago,
Okay?
if you had a shorter barrel, the time obviously would be shorter than the forces applying on the bullet.
Correct. Less time applied.
The reaction would be different for the gun. The gun would realize reaction over a period of time that corresponds to the T for the bullet. Am I making myself clear?
Yes, I think I see what you're getting at. Let's do it here. I can't draw a cannon. Let's see. Here we go. If it was a short barrel versus, a long barrel. Whoop. Or starting here versus starting there. The force that the barrel applies is from the gunpowder, and it'll still be the same whether you put it here, there, short barrel, long. This can only provide so much force. That's applied for a certain amount of time, and I think you all see it now that if it starts here and has a long barrel, T will be bigger than if it's a short barrel or it starts over here. Still with me to that point? So the recoil comes from conservation of momentum. But before I get there, both cases, the force is the same there as it is if it's there. Thus, in this action-reaction pair, the cannon exerts a force on the cannonball exerts the same force back on the cannon. Same game here. Force on the cannonball back on the cannon, but it's the same force. The key here, again, is that time. If this one's applied for a larger time, then the impulse is bigger and there's a greater change in momentum, and the cannon is going to want to recoil more. It'll have a greater change in momentum shooting back. In other words, if it was this case and we made this longer, you would see this moving more quickly. The total momentum is still 0. That's just like upping some of these. Let's see. Okay, we can make this 2. So now if this is 2, this has to be 2. This would be going 20 meters per second to still keep total momentum conserved. But both would be going faster. You would see that effect of the recoil with the longer cannon because it received a greater impulse. Gets a greater change in momentum. But the total momentum is still conserved. I have to compliment you guys. I really do. You're showing that you're thinking this through and you really want to understand it. I applaud that. You'll get more out of this in not just the class, but your whole life, I hope. The fact that you're trying to work this through. I hope you don't see this as a hindrance. Oh, come on, Adam. The clearer this is, the better you'll be able to apply it to real life. And in my mind, that's the point of this class, not to just get a credit for your whatever. Did that help you, sir? Because you definitely will feel the recoil more if you have a longer barrel. And it's because of the impulse. Back to this one. I said I'd do a number. Let's do it. So it's a force for a certain amount of time, or a force for a larger time. This will be the greater impulse and have a greater change in momentum. So we'll do it like that. Which is mass times velocity. It's going to change it. We're not changing the mass, so this one gets a little velocity and this one gets a big velocity. So we could put in whatever the mass of the marshmallow was and figure out the muzzle velocity by just timing. It's a little more harder to do right here, but you get the idea. So bottom line out of all this is to differentiate between impulse, force, and momentum. They are different. Let's do another one. And yeah, one more. We're on it. We'll get to you. Not yet. You're next. Because I like this one. I think it'll help. I hope. All right? That one. So this is that. Fast-moving car hits a haystack, or, separate case, it hits a cement wall. Let's see if you're getting this. Do they have the same change in momentum, same impulse, same force, or some, not all? The car is moving. It has momentum. It's going to run into something and stop. But one's a wall, and the other case is a haystack. What differs, what doesn't? You can talk to your neighbor. It's fine. I don't know where it went. Okay, you got 30 seconds and it'll shut off. Close you out. 30 more seconds. Ten seconds. Get it in if you want to vote. 2, 1. Most of you think answer B. 52%. The others are about equal. So yes for 1 and 2. The correct answer is B. Good for you. So again, if you're going a certain speed, you're coming in with the same momentum in each case. Initial momentum. You're going to stop either way, within reason. And so your momentum is going to go to 0. So your change in momentum should be the same in both cases. You're going to be going yay fast and stop. Same change in momentum. Change in momentum is impulse. And impulse is what's going to cause that change in momentum. To create the same change in momentum, you will need the same impulse. So, 1, do you experience the same change in momentum? Yes. Same impulse? Yes. Do you both experience the same force? And that's the one that is different. Because in order to have that same impulse, same change in momentum from whatever speed to 0, running into this will do it more quickly. So t is little, which means the F, the force, needs to be big. The force on the wall and the force back on the car will be large. For the haystack, that can extend the time of collision. The t will be longer. The force does not need to be as big. The product still has to be the same. The impulse has to be the same to have the same effect on the car to stop it. But you can use less force if you do it for a longer period of time. Okay. Oh, do you have a question?
I'm confused about force and impulse still. I thought force was going to be the same because the car was going same amount of speed. But the time, doesn't time have to do with impulse?
Time does have to do with impulse.
When you hit the haystack, it takes you a longer time to slow down, right?
Correct. It will take a longer time to slow down when you hit the haystack, yes.
Okay, so then how would the impulse be the same?
The impulse is the same because look at change of momentum. Impulse is change of momentum. They will have the same change of momentum because they come in with the same momentum, mv, and they're going to end up at m0, no velocity, so no momentum. So the change in momentum in either case will be the same, which means the impulse has to be the same because that's what impulse is, change in momentum. And now in order to provide that impulse, one does it for a long period of time, thus it needs less force. And one does it for a short time, needs more force to provide that same impulse, to have the same change in momentum. The force between the car and the brick wall will be larger than between the car and the haystack. All right, we have somebody that's willing to help me out with a demo. I'm proud of him. You're on. Explain what we're going to do.
Okay, well, I came up to Professor Beehler last class and I explained to him that physics has a lot to do with my job, which is teaching martial arts. And as I heard some of the principles of Newton's laws, it made some of the things that we do make a lot more sense. And so I thought it would be neat for us to do a couple little demos. So we'll first do the redirecting demo.
Okay.
Okay, so in martial arts, there are many ways to defend yourself, right? If someone's stepping up to punch me in the face, I could use a blocking technique, which is a large amount of force, sorry.
That was for emphasis. It did hurt though.
Over a short period of time. So that works well because we're both about the same size. But let's pretend Professor Beehler's huge.
Pretend.
And I'm kind of tiny, right? Well, using a blocking technique like that might not work as well because I can't exert that much force. I can still defend myself. So as he's stepping up to punch, I can use less force but more time.
Slow-mo.
Right? And then I still am able to defend myself. I still get him to move out of the way. I still stay safe. Right? And I'm actually using his momentum against him.
Again. I'm already moving forward. He's just redirecting it.
Yes. So I don't have to have that much force if I extend the period of time.
Do you see it? He grabs on and pulls. So the time's bigger, force doesn't need to be as large. As opposed to, just boom. That's just a quick one, and you can feel it.
Yeah. So the time is shorter, but I need more force. So both ones work, but depending on how much force you want to exert.
So that's a case where it's the same change in momentum we're trying to result, thus the same impulse, but you can play with force and time to produce that same result. But if you're not impressed yet...
So this next one, I brought some pine boards. When we break boards in Taekwondo or any other martial art, how the person holding the board holds it is very important. Right? If I want to break this board, it's it's important that he stays steady. remember when Professor Beehler was talking about hitting the bag versus hitting the paper? You can't exert very much force on the paper because the paper can't exert very much force back in your hand. It gives in.
Like this. Don't actually break it.
So this time, if you,
Slow-mo, fake.
if you gave in,
But if I flinch,
right, boom, then I'm not able to break it. And when we break boards at like black belt testing or things like that, if the board holder isn't steady, you know, the person hitting might actually get hurt because they follow through and they hit their hand on the edge.
One of the first things he told me was, okay, I'll do it, but you need to hold it. And right when I hold, flex! So that I don't do this, and he can't break it.
Yeah.
Okay.
Did you want to break one?
I never have. Well, okay.
Okay.
I won't lie, I'm nervous. How do I hit the board?
All right. You're right-handed?
I am.
Put your right foot back. Okay.
I just want to, what position am I in when I contact the board?
You're going to have your palm hit right there. And
Okay.
as long as you follow through with all your momentum, right, you have enough velocity, you have enough mass, that you'll break it.
And why do you want to follow through? It increases the impulse. I can just stop right there, certain force, short time, or I can do the same force and try to follow through a little bit while it's braking. Extend that time and increase the impulse. Same force for more time.
All right. So a little practice for a sec.
That's fine.
So go ahead and put your right hand against your side. Now you're going to make it go straight forward. If you come out, you're going to lose some of that.
Like that?
Exactly.
I'm practicing.
Okay. Let's see. Go. Good. Again. No problem. Ready? Go.
This is fake. Hold on. Okay. I never have done this. Okay. Got camera? Yep, I'm scared. Here it comes.
Nice.
Woo. Thank you.
You're welcome.
Wow, thanks. That is empowering. So you don't have to break boards, but if you're going to hit somebody that's attacking you, I hope you know how to hit them now. Wow. Oh, that's cool. Thanks. I'm stoked. Sweet. It didn't break. All right. I got to get more of those boards now. All right, let's give you a few more examples to go think about. These are the same mass. So if I try to have this one not moving much, by the time this one runs into it, I'm going to go like this. It's going to come back and hit this guy. Before the collision, what's his momentum? His? mv. After the collision, okay, so the total momentum of the system is? Before the collision. 0 and mv, so the total is? mv of the system. After the collision, what should the total be? mv. The total has to stay the same, conservation of momentum. This guy is going to impart an impulse on him. They're going to change each other's momentum. What do you think will happen? Will he bounce off? Will they both move? Will he stop and this one move? Here goes. It's not exactly level, but you get the idea. Boink. Essentially it comes to a stop. If they're the same mass, then before the collision and after the collision, they just transfer momentum from one to the other. But the total stays the same. I got one. I'll bring it out at some point. So, M, V. Before the collision, the total momentum is mv, we'll do positive, plus mv, 0. So it's mv. You follow that part? Doesn't hurt as much as I thought, but it still hurts. After this one comes to a stop, and he gets moving. So it's mv, 0, plus mv in the positive direction. Do you see that the total is still mv again? So if I do a smaller one, now what will happen? Less mass. For argument's sake, it looks close. This is half the mass. So if this guy comes in, he's got momentum mv, and they hit, the total momentum of the system has to be, but what will they do individually? This one will go faster. Will this one stop? He's bigger. He slowed down. Did you notice that? He comes in, certain velocity. When he hits, he goes slower because some of his momentum was transferred to this guy. Boink. So that's like big M, big M, big M. So the total momentum before the collision is big mv. After the collision, the total has to be big mv. But we have big M going at a little less velocity, and this guy doesn't get going as fast as he did before, but a bit. And it's hard to represent. The ratio is 1 to 2 here. Plug in some numbers. Let's see. Let's say this is a kilogram. It's not what I want to do at this point, because I want to show you something else. But you could just plug in some numbers. You'll see how it works. We can do it again next time if you get stuck. But since this one is half the mass as this one, he will be going twice the velocity of this guy afterwards. And you can prove it to yourself, or we can do it later. Let's do a different one though, just so you can see a few of these. Help you visualize. Let's try to get them going the same velocity, roughly. When they come back together, doink, they come off. But you can have all kinds of collisions. What if this one's going slowly and this one's faster? He slowed down, he picked up speed, transfer of momentum. But the total before and after always have to be the same. How about this case? This guy is going to be still, and the little guy comes in. Will the little guy stop? I hope you know this guy won't be moving super fast. Who do you think will be moving faster at the end? The little guy. Will he be moving as fast as he was initially? No, because he transfers some of his impulse momentum too. So here we go. Yeah, he slowed down, but he bounced off. He didn't stop because they have different masses. And you can work it out. That's where conservation of momentum comes in handy. You can solve all kinds of things. And these, one more, and I'm done, were elastic collisions. Elastics where they bounce off, rebound. Inelastic is where they stick. So I got some Velcro. So if I do this and it comes in and it sticks, it can't bounce, so what will happen? They're going to stick together. The total mass increases of the system. It doubles, in fact. And so they go half the speed as the incoming one was. But the total momentum is still conserved if you work it out. Thanks. Certain speed, nothing. Momentum, combined momentum, half the speed. Combined mass, half the speed.